Hello, welcome, welcome, welcome. So today we are going to be doing Coulomb's law. Let's get right into it. So, what is Coulomb's law? Coulomb's law is the electric force between 2-point charges and is given by the equation below. I'm going to find a better one, but we're basically finding the electric force felt between these two charged points, right? So let's find that really quickly. Here we are. And it's given by this equation, Coulomb's constant times charge of point charge 1 times the second charge divided by the distance separating them. Some key points, the force or the electric force can be attractive or repulsive. So the electric force can either push or pull. Next, Q1 and Q2 are charges that are measured in coulombs. So that's our unit for charge. Keep that in mind. R is the distance between the charges, right? The distance here to there. And it's measured from the center of the nucleus of one to the nucleus of the other, or just the center. And it's also usually in meters, so you want to keep that in mind when you're doing your calculations. Now, K is Coulomb's constant, which is into sig figs 9.0 times 10 to the 9 newtons per meter squared per coulomb squared. So this is a big, big number, but you can easily derive it by just looking at this. So we have charge 1, charge 2, this is charge times charge, which is coulomb squared, times meter squared. And if we just flip it, what you're going to get? You're going to get meter squared over coulomb squared. And there you are, meter squared over coulomb squared, and this Newton, we put it there, and this is what gives us the force, right? Newtons times these things that cancel out will just leave us with newtons, and that gives us our force. Anyways, signs of force. If it is a positive force, we are going to see some repulsion. So it's either between two positive or two negative charges, right? There we are. And if it is a negative force, we are going to see some interaction, and it's going to be in between opposite charges. So that's what you want to keep in mind. And next, we have Coulomb's law versus universal law of gravitation. What we're going to notice is that the law of universal gravitation is very similar to Coulomb's law in the fact that it has divided by the distance between the centers of the two entities being analyzed, and they both get a force. However, the difference is their constants. This is a gravitational constant, this is Coulomb's constant, and we are analyzing masses here, so kilograms is the unit, and we are measuring or analyzing the charges here, or coulombs, which is our unit. So notice that both follow a square inverse relationship, right? Look here, d squared. F is proportional to d squared, or 1 over d squared, so it's an inverse square relationship. Both forces act along the line joining the centers of the two objects, that's another thing you want to mention, and distance r is measured from center to center in both formulas. Now, the difference is that electric forces can either attract or they can repel, so they can pull or push, but gravitational force only attracts towards itself. Now, gravitational constant g is very, very small, while k is very, very, very large. So I'm going to paste this and you can see it. Here we see the gravitational constant, 6.6 times 10 to the negative 11 versus 9 times 10 to the 9. Obviously, that is quite a bit of magnitudes larger. I believe around 20 magnitudes. So definitely noticeable. If there is motion or if there is rest, their force is going to change. But for here, whether the masses are in rest or in motion doesn't really matter. Now, something important you want to note is that most objects are electrically neutral because positive and negative charges will just balance out, right? Therefore, electric forces will usually cancel. However, gravity never cancels, which is why it dominates on large scales in the universe, while electric force is not really noticeable. So while gravity can't cancel out, electric force can, right? If we look here, attracting or repelling, and overall these attractions and repulsions will equate to no, like electrically neutral. Next, we have charge and the coulomb. So scientists group charges into units that are called coulombs. 1 coulomb is equal to that many electrons, and the charge of 1 electron is 1.602 times 10 to the negative 19 coulombs. So you have 1 little electron, and it contains this many charges. It is very small, though. Please notice that. And the total charge on an object is equal to Q times N times E. Now, what does Q mean here? So Q is the total charge. That's what we're trying to find here. Then we have N, which is basically the number of electrons that you gain or lose. So our deficit or excess, say you gain 3 electrons, and you have this, which is the charge of 1 electron. This is our constant. So I'm just going to note that here. Constant. There we are. So we have a constant multiplied by the number of electrons, and we get the charge. So if we have 1, we're going to get this number. 2, we get 2 times this number. 3, you get it. So we have an example, right? Effect of changing distance and charge. So we are given an initial force of this, and we're going to triple the distance. What happens? Well, let's look at our formula, right? Force becomes 1/9 of the original. Why is that? Well, think about it. If you triple the distance, you triple what you're dividing by, right? And what's 3 to the power 2? 9. So your original values divided by 9 will give you 1/9 of your force. So your new force is going to be that. Now, one charge is quartered, the other is doubled, so the force becomes 1/2 of the original, right? 1 is quartered, so 0.25, 1 is doubled, you get 0.5 if you multiply it quarter by 2, and that's what the force becomes, 1/2 of the original. because we get that 0.5 factor. And what happens if both change together? So the force becomes 1/18 of the original. What we did here is we're just saying, oh, we're pairing B, the effects of B and A, so 1/9 times 1/2 is 1/18, and that's going to be our new force. Now, example 2, transferred electrons. So we are given 3.7, blah, 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 electrons are transferred. So we're giving transfer, or we're transferring electrons to something. And remember how n is the number of electrons we're adding or taking away. So we multiply this number right here by the constant charge of an electron, and this is the charge that we get of the transferred electrons. One object is going to have this amount, and one is going to have that, because one is gaining electrons, so it will become more negative, and one is losing electrons, so it becomes way more positive. Now, what happens if we have multiple charges? So Coulomb's law only applies to 2-point charges at a time, and for systems with more than 2 charges, we gotta calculate the force between each pair separately. This can become tedious, but it's essential in order to tackle these problems. We also want to add forces using vector addition. Ooh. The result is the net force on the charge. Now, we're going to look at example 3, 3 charges in one dimension. So we have these charges, 3.6 microcoulombs, this and that. Microcoulombs, remember, is going to be, what is it, 10 to the power of what? -6. So we have 3.6 times 10 to the -6 coulombs, and so on. What we want to do first is we want to choose a notice that we have 3-point charges, Q1, Q2, Q3. And we are going to go through the solution together. Okay. We can see that there are 30 centimeters separating Q1 and Q2, and then 20 centimeters separating Q3 and Q2. We're going to let right be the positive direction, and in one-dimensional problems, the vector sum and the arithmetic sum are the same, so we just want to add up these forces, and the sum is going to equal the total force. Now, let F net 3 represent the net force on Q3. We want to find the total charge of Q3, so that's why we're solving for it. So we're going to say F net 3, and then F13 represents the force of charge Q1 on Q3. Notice that the distance is 30 centimeters plus 20 centimeters, right? So 50 centimeters. Be aware of that. Whenever you're doing these types of calculations, always ask yourself, how far is a distance truly? Now we also have F23, which represents the force of charge Q2 on charge Q3. We are going to add up the net force here and there, and notice that this is the vector, so F net 3 equals this times that. We're adding our vector symbol, and then when we're looking purely for the magnitude, we're going to consider the direction. Is it positive? Is it negative? Is it attracting? F13 is positive, so its charge is positive. This is positive. We know there's going to be repulsion. It's going to go like this, and it's going to push. So that's why we see here in our vector diagram that it's facing that direction. However, if you look at charge Q2, you're going to notice it is negative. It's going to pull this positive towards itself, which means it's going to point in this direction. Very good. And when we look at the magnitudes, we are going to consider these directions. So F13 is going to be in the positive direction, and F23 is going to be in the negative direction. Now, we are going to then put our formulas in here. We're going to simplify it a little bit for us and take out any charges that are same or any other variables that we could just do once instead of twice. So we take this out, or factor it out, and then we're left with this times that, and then times this where it's still the negative sign, and our result is going to be -2.2 newtons. You always want to make sure that the sig figs are right, so 2 sig figs, 2 sig figs, 2 sig figs, and total force, so yes, newtons. And since force is a vector, you're going to also want to put the direction, so never forget to put direction for vector quantities, unless otherwise asked. Now we're going to move on to our third question, which is 3 electrons are distributed as shown in the diagram below. Find the net force acting on electron Q1. So this is going to definitely need a vector diagram, and we know that force is a vector, so we don't get it easy. Let's do it. So what you want to say is that our charges are equal to each other. You want to express that explicitly. And what's next is you want to say that R21 equals R31, right? It's an equilateral triangle, so this automatically gives us our angles. Whoa, music. And it gives us our equilateral triangle, and since the magnitude of charges and the distance between them are the same, force on Q2 is the same as force on Q. What you can understand is that since the charges and the distances are exactly the same, as well as their angles, which I believe is important to mention, although it's not said here, the force on Q1 exerted by Q2 is the same as the force of Q3 acting on Q1. So we can express that F21 equals F31. And all we have to do is plug in our values, and we are going to find the magnitude of the forces. Now, what we want to do is we want to figure out what is the net force, and now we have to consider our dreaded angles. So let's look at this triangle really quickly. Compare them. So we can tell in this triangle. Okay, so we have 1, 2, 3, right? And we know they're all going to be positive, so we want to see how is it acting on electron 1. Q3 is going to be pushing this way, Q2 is going to be pushing that way. Now, how do we know these angles? How the heck do we know that? Well, what we can do is we can figure out this. Equilateral triangles always have internal angles of what? 60 degrees, right? And we know, based on relations to triangles, this is going to be 60. This is going to be 60, right? 60, 60. We'll add the little dot. And then this must be what? 30. And that's how we got this, and that's what we're going to use to find the forces. Now, F net1 equals F21 plus F31, right? And we are going to use the law of cosines to avoid those pesky components. And what we can see here is that f squared of 21 plus f squared of 31 minus 2f21 f31 cos theta. And theta is obviously not 30. No, 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 no. If you think it's 30, be very, very careful. Because what we're doing, we're actually taking this and we are placing it right on top. And what that means is that, well, this is going to be 60. We know that this is going to be 30. This is going to be 60. And as a result, it is 120 in total. So that's how we got cos 120. Always be careful and always remember, maybe add it up. You can always draw 120, and there you go. And this is our net force, if you plug that in. And we know that their x components are going to cancel because they are equal. So F net 1 is only in the y direction, and that's why my teacher just went straight to F net 1 and didn't use net y or anything like that. Therefore, the net force acting on the electron must be in the vertical direction, y direction, whatever you call it, and is 7.1 times 10 to the negative 24 newtons up. Key ideas: remember that forces from two electrons are going to always be... Nope, ignore me. The forces in this question, specifically, show that the forces are equal in magnitude, right? Because they're two electrons, they're the same charge. Now, horizontal components cancel out, and because of that, only vertical components will add, and that's our net force. To summarize this lesson, Coulomb's law describes electric forces between charges. Also, force depends on charge size and distance. Next, direction depends on attraction or repulsion. And lastly, for multiple charges, we use vector addition, especially in those 2D examples. Thank you so much for watching. If you click on the link below this video, there will be a section here that will lead you to a little quiz. So try it out and have a lovely, lovely day. And remember to always spread kindness. Bye!